ALMA just detected something wild in 3I/ATLAS. This interstellar visitor is loaded with 124 times more methanol than any comet we've ever seen. What kind of frozen hellscape births something like this? Scientists now believe it came from a region so brutally cold and chemically extreme, it challenges everything we thought about how planetary systems form. Are we looking at proof that the Milky Way has icy nurseries, far stranger than our own? Let's dive right in. So what exactly did ALMA find that has scientists rethinking everything? Let me walk you through this discovery, because the details matter, and they're absolutely fascinating. Chile's ALMA radio telescope array locked onto 3I/ATLAS between September and October 2025, right as this interstellar wanderer was heating up near the Sun. Radio astronomy is our most powerful tool for studying chemical composition, because when radio waves pass through a comet's coma, that fuzzy atmosphere of gas and dust surrounding it, they capture the precise molecular fingerprint of everything present. No guesswork, just pure data. The first thing ALMA detected was hydrogen cyanide, or HCN. This was completely expected. Every comet we've ever studied contains HCN. It's the baseline, the common denominator. Think of it like finding water on Earth. It's just there. Scientists use HCN as a reference point because it's so universal across comets. Then came the methanol readings, and that's when everything changed. The methanol to HCN ratio in 3I/ATLAS measured 124 times higher than anything we've ever seen in our solar system's comets. Not 10% higher, not double, not even 10 times. 124 times. That's not a variation. That's a completely different chemical recipe. Now, you might be thinking, okay, so it has more methanol. Why does that matter? Here's why this number is so significant. Methanol doesn't appear randomly in space. It freezes at specific temperatures, slightly warmer than other volatile molecules. Finding this much methanol tells us something profound about where 3I/ATLAS was born. It came from a region of its home star system that was brutally, extraordinarily cold. Colder than our Kuiper belt, colder than our Oort cloud. We're talking about a planetary nursery with temperature conditions so extreme that molecules condensed in proportions we've never witnessed. But ALMA didn't just measure what molecules were there, it revealed something even more intriguing, where these molecules were coming from on the comet itself, and the answer completely defied expectations. The hydrogen cyanide, it's sublimating directly from the nucleus surface in a concentrated, localized region. Clean, predictable, exactly what you'd expect from standard cometary activity. The methanol, it's everywhere, distributed widely and diffusely throughout the coma. More importantly, it's not coming from surface sublimation. It's being released from ice grains that are violently ejected during explosive outbursts, like geysers erupting from the comet's core. These aren't gentle releases. We're talking about powerful jets of material blasting into space, loaded with methanol-rich ice particles. What this tells us is absolutely crucial. The nucleus of 3I/ATLAS isn't a uniform ball of ice. It's a complex layered structure with different chemical zones behaving in completely different ways. One region releasing gases gently from the surface, another zone triggering explosive ejections of ice grains. This level of internal complexity raises immediate questions. How did this structure form? Was the comet assembled from materials that originated in different parts of its home disk? Did billions of years of interstellar radiation create these distinct zones? Every answer leads to more questions, and that's exactly what makes this so exciting. Understanding where 3I/ATLAS came from means reconstructing the environment of its birth. In our solar system, we have a fairly organized picture of how things formed. Close to the young sun, temperatures were high. Only rocky materials and metals could condense. Move outward, water ice became stable. Further still, carbon dioxide ice. And way out in the frigid outer reaches, methanol started appearing in significant quantities. There was a chemical gradient, a predictable pattern based on temperature zones. But 3I/ATLAS's home system, the rules were different. That extreme methanol abundance points to a protoplanetary disk region that wasn't just cold, it was a deep freeze with a chemical environment unlike anything in our solar system's formation history. This was a zone where methanol didn't just appear, it dominated, overwhelming other volatiles in proportions we've never seen. Maybe that star was dimmer, keeping the outer disk frigid. Maybe the disk itself was more massive or extended, allowing for chemical processes we don't see in our own history. Maybe the starting materials, the elemental abundances in that molecular cloud, were fundamentally different from what built our sun and planets. The truth is, we don't have all the answers yet. But every measurement, every spectrum, every data point from 3I/ATLAS is forcing us to expand our understanding of how planetary systems form across the galaxy. And that brings us to perhaps the most profound realization from this discovery. For decades, we've studied comets, asteroids, meteorites, every rocky and icy body we could get our instruments on. But all of them came from here, from our solar system. We built models of planetary formation, refined our theories, and created what we thought was a comprehensive picture of how star systems develop. Sure, we acknowledged there might be variations, but we assumed the basics would be the same everywhere. Similar chemical gradients, similar proportions of key molecules, similar rules. 3I/ATLAS just showed us how limited that perspective was. If one interstellar visitor displays a 124-fold difference in a fundamental chemical ratio, what else is out there? How many thousands of different planetary nursery configurations exist across the Milky Way? What does this chemical diversity mean for the planets that form in these systems? If the building blocks are so radically different, are the resulting planets equally varied in ways we haven't even imagined? This isn't just about one weird comet. This is about understanding that our galaxy is not a cosmic assembly line stamping out identical solar systems. It's a laboratory of infinite variation, each star system with its own chemical personality, its own formation story. We're only beginning to glimpse this diversity, and it's humbling. What makes this moment special is that we're not studying ancient history from incomplete records. We're tracking 3I/ATLAS in real time as it travels through our solar system. Unlike Oumuamua, which we spotted as it was already leaving, or Borisov, which we caught late in its passage, we've been watching 3I/ATLAS since it entered. That means complete data collection across its entire journey through our neighborhood. December 19th marks its closest approach to Earth, about 270 million kilometers away, nearly twice the Earth-Sun distance. That's not exactly close, but it's close enough for every major telescope on the planet and in orbit to maintain observations. And they will. Every observatory that can point at 3I/ATLAS is gathering data, adding pieces to the puzzle. After Earth, this cosmic traveler continues its journey. It already passed Mars. Next stop is Jupiter in March 2026, where the giant planet's gravity will give it one final gravitational interaction before 3I/ATLAS heads back toward interstellar space. And throughout this entire trip, scientists aren't letting up. Every observation session adds detail. Every spectrum reveals nuance. By the time this comet disappears beyond Jupiter's orbit, beyond the reach of our instruments, we'll have assembled the most complete biography ever compiled of an interstellar visitor. Let's talk about what that methanol signature really represents, because this is where chemistry becomes a time machine. Methanol forms under specific conditions, certain temperatures, certain pressures, certain chemical environments. Its overwhelming presence in 3I/ATLAS is like finding a message in a bottle, except the message describes the ocean it came from. If you map our solar system's chemical layout during formation, methanol would be most abundant in the coldest outer regions. But even there, it wouldn't dominate the way we're seeing in 3I/ATLAS. This implies a formation zone that was either dramatically colder than our outer solar system, or had different starting materials with more carbon and oxygen available in molecular forms that favor methanol production over other compounds. Some researchers are speculating 3I/ATLAS might have formed in the distant reaches of a system around a low-mass star, where temperatures stay perpetually frigid even during active planetary formation. Others wonder if it originated in an unusually dense region of a protoplanetary disk, where molecular chemistry could proceed along different pathways than in our sun's disk. These aren't wild guesses. They're hypotheses grounded in what we know about chemistry, temperature, and molecular formation. Each possibility opens new questions about the diversity of environments where comets and planets can form. We've now encountered 3 interstellar visitors: Oumuamua in 2017, Borisov in 2019, and 3I/ATLAS in 2025. Each one taught us something different, and together they're painting a picture of just how varied interstellar space really is. Oumuamua was the shock, strangely shaped, tumbling unpredictably, showing acceleration that couldn't be explained by normal outgassing. We still debate what it really was. Borisov brought relief. It looked like a normal comet, confirming that familiar objects exist in other star systems too. And now 3I/ATLAS gives us something in between. Definitely a comet, no question about that. But with chemistry so extreme, it challenges our models of what's chemically possible in planetary formation. The fact that 3 random visitors show such different characteristics tells us something important. There's no such thing as a typical interstellar object. These are the only 3 that happen to pass close enough to Earth for us to detect and study. Imagine the countless others drifting through the Milky Way that we'll never see, each one carrying its own unique story, its own chemical fingerprint from whatever distant system created it. Every week brings new data from 3I/ATLAS. Telescopes continue tracking it, spectroscopes continue analyzing its light, radio observatories continue mapping its molecular emissions. This is science happening in real time, and by early 2026, when 3I/ATLAS fades from view, we won't just have snapshots. We'll have a complete documentary of an alien world's messenger passing through our cosmic neighborhood. What that documentary reveals will tell us not just about one comet, but about the staggering chemical creativity of the universe itself, about formation environments we've never witnessed, about the thousands of ways planets and planetary systems can begin their existence. And that knowledge is priceless. So here's what 3I/ATLAS really means. Our solar system isn't the blueprint for the universe. It's one recipe among millions. That 124 times methanol reading is hard evidence that planetary nurseries across the Milky Way form under wildly different conditions, some colder, some with completely alien chemistry. And if the building blocks are this different, imagine what kinds of worlds are forming out there. This comet is still traveling toward Jupiter right now, and scientists are capturing data every single day. By March 2026, we'll have the most complete profile ever of an interstellar visitor. But the real story isn't just what we've learned, it's how 3I/ATLAS has changed the questions we're asking about planet formation everywhere. What will the next interstellar visitor show us? Because they're coming. Our detection capabilities mean we'll spot 1 or 2 per decade now. Will the next one have chemistry even more extreme? Will it shatter our models again? If you want to stay ahead of every breakthrough like this, subscribe to Galactic Breaking News and hit that notification bell. We're covering every major space development as it happens. Drop a like if this discovery blew your mind, and comment below. Do you think the next interstellar object will be even stranger? And don't miss our latest video on SpaceX's Starship Phi-3 challenges, because while cosmic visitors pass through, humanity's racing to become an interplanetary species. The universe is revealing its secrets. Let's discover them together.